From this point on, I will walk you through Tesla's full self-driving system and the advanced safety technologies built into the vehicle. This slide gives us a high-level overview of how Tesla thinks about autonomous driving and safety. At the core of Tesla FSD is a vision-only architecture. Instead of using radar or LiDAR, the car relies on a network of cameras, more than 8 in total, to see and understand the world around it. These camera feeds are processed by neural networks, which make sense of the environment and support real-time driving decisions. FSD is not a static system. It is continuously improved through over-the-air software updates. That means the same hardware in the car can become smarter and safer over time as Tesla refines its models and releases new versions. The goals of FSD are ambitious. Tesla aims for driving behavior that feels as natural as a skilled human driver. The system is designed to assist across both city streets and highways, with a long-term vision of becoming the foundation for a robotaxi platform. But FSD is only one part of the safety story. Tesla vehicles combine active safety and passive safety to provide a high level of protection. Active safety features are designed to help prevent accidents. These include automatic emergency braking, lane departure prevention, blind spot detection, side collision avoidance, and vision-based hazard detection. All of these systems work together to reduce the likelihood of a crash. Passive safety focuses on protecting occupants when a collision does happen. Tesla uses an ultra-high-strength body structure, carefully engineered crumple zones, and a robust battery protection structure. The low center of gravity improves stability, and a multi-airbag system helps protect passengers from multiple angles. In summary, Tesla FSD is built on a vision-only AI stack, and it is tightly integrated with both active and passive safety systems. Together, they form the foundation for Tesla's long-term approach to safer, more autonomous driving. In this slide, I will explain Tesla's vision-only architecture and why Tesla decided to remove both radar and LiDAR from its vehicles. Tesla's full self-driving system relies entirely on camera-based perception. The idea is simple. Humans drive using vision, so Tesla believes that AI should learn to drive the same way. The vehicle is equipped with 8 to 11 cameras depending on the hardware generation. Together, they provide full 360-degree surround vision. At the front, Tesla uses a triple camera setup, which includes an ultra-wide lens, a wide lens, and a telephoto lens. Side-facing cameras monitor the left and right lanes, a rear camera watches behind the vehicle, and a cabin camera is used for driver monitoring. Now, let's talk about why Tesla chose a vision-only approach. Radar can introduce noise and inconsistency, especially in close-range detection. LiDAR is accurate but expensive, and it does not scale well for mass-produced consumer vehicles. Tesla also found that neural networks perform better when they are trained on a single, unified visual data stream. By simplifying the hardware, Tesla can iterate on software more quickly and improve the system at a faster pace. There are also important technical advantages. A vision-only system enables end-to-end neural network training. It reduces the complexity of sensor fusion, and it improves the prediction of object behavior, including vehicles, pedestrians, and cyclists. In summary, Tesla removed radar and LiDAR to focus on a pure vision-based approach, one that mirrors human perception and allows the AI system to learn and improve through large-scale neural network training. In this slide, I will walk you through the evolution of Tesla's hardware platform from HW1 to HW4 and even beyond. Tesla's hardware has continuously evolved to support more advanced neural networks and real-time perception for autonomous driving. Each generation brings stronger computing power, better camera systems, and improved support for end-to-end AI models. Let's begin with HW1. Released between 2014 and 2016, HW1 was based on Mobileye technology. It supported basic lane keeping and traffic-aware cruise control. This was Tesla's first step toward assisted driving. Next came HW2 and HW2.5, released from 2016 to 2019. This was a major shift. Tesla introduced its own in-house computer and added an 8-camera setup, laying the foundation for a vision-based autonomous system. Then we moved to HW3, released from 2019 to 2023. This is known as the Tesla FSD computer. It delivers 144 TOPS of performance, which allowed Tesla to run early end-to-end neural network models directly inside the vehicle. Now we arrive at HW4, which is the current generation. HW4 includes higher resolution cameras and more than 250 TOPS of compute power. It is specifically designed to support Tesla's FSD versions 12 through 14. It also features improved thermal management to handle the increased processing load. Looking ahead, Tesla is developing HW5. This next generation platform is expected to exceed 1000 TOPS, and it is optimized for large-scale robotaxi networks. Future versions may also increase the number of cameras from 8 to as many as 12. Now, let's briefly discuss why hardware evolution matters. Higher compute power allows Tesla to run more complex neural networks. Higher resolution cameras improve perception accuracy. Faster inference leads to smoother and more natural driving behavior. And most importantly, Tesla's hardware and software are designed to evolve together to maximize FSD performance. In summary, Tesla's hardware has progressed rapidly from HW1 to HW4, and HW5 is expected to push the limits even further. Each generation brings more computing power, better perception, and stronger support for Tesla's long-term vision of fully autonomous driving. In this slide, I will explain Tesla's overall safety architecture, which combines active safety systems with advanced passive safety engineering. First, let's look at active safety. Active safety features are designed to help prevent accidents before they happen. Tesla vehicles include automatic emergency braking, which can detect an imminent collision and apply the brakes to reduce impact or avoid the crash altogether. Forward collision warning alerts the driver when the car detects a high risk of impact with a vehicle or obstacle ahead. Lane departure avoidance helps keep the car within its lane by gently steering or warning the driver if the vehicle begins to drift unintentionally. Blind spot monitoring watches the areas that are hard for the driver to see and warns when another vehicle is in the blind spot. Side collision avoidance can apply small steering inputs to help avoid a vehicle that is too close on either side. Traction and stability control work together to maintain grip and balance, especially on slippery roads or during sudden maneuvers. On top of these features, Tesla uses vision-based hazard detection and real-time neural network predictions. The cameras and AI continuously analyze the environment, predict the behavior of other vehicles, pedestrians and cyclists, and support quick, informed reactions to potential dangers. Now let's move to passive safety. Passive safety features are designed to protect occupants when a collision actually occurs. Tesla vehicles use an ultra-high-strength steel frame, which helps maintain the integrity of the cabin during a crash. Front and side crumple zones are carefully engineered to absorb and dissipate impact energy before it reaches the passengers. A rigid passenger safety cell surrounds the occupants, providing a strong protective structure around the cabin. The battery pack is also part of the structure. It is protected by a dedicated housing, which helps shield it from damage and adds rigidity to the vehicle's body. Multiple airbags, including front, side, and curtain airbags, are positioned to protect occupants from different directions in a crash. Because the heavy battery is mounted low in the chassis, the car has a low center of gravity. This reduces the risk of rollover and improves overall stability. Tesla vehicles consistently achieve high crash test ratings globally, reflecting the strength of their passive safety design. Finally, let's summarize why Tesla scores so high in safety. First, Tesla integrates software and hardware from the ground up. The active safety systems, sensors, and vehicle structure are designed to work together as one system. Second, real-time over-the-air updates allow Tesla to improve safety features even after the car has been delivered, enhancing performance and response over time. Third, the structural battery pack increases body rigidity, which improves crash performance and overall vehicle stability. And fourth, the vision-only system combined with powerful neural networks helps the car react quickly to changing road conditions and hazards. In summary, Tesla's safety architecture brings together advanced active safety software and industry-leading passive safety engineering. Together, they provide a high level of protection for everyone inside the vehicle and for other road users as well. In this slide, I will explain the difference between Tesla Autopilot and Tesla Full Self-Driving, so you can clearly understand what each system is designed to do. Let's begin with Autopilot. Autopilot is primarily focused on highway driving. It includes traffic-aware cruise control, which adjusts the car's speed based on the vehicle in front. It also includes auto steer, which keeps the car centered in its lane. Autopilot works best on structured and predictable roads, such as highways and expressways. Even with Autopilot active, the driver must always supervise the system, keep their hands on the wheel, and remain ready to take control at any moment. Autopilot is an advanced driver assistance system, not an autonomous driving system. Now let's move to full self-driving, often called FSD. FSD is designed for much more complex environments, including city streets. It can navigate through intersections, handle unprotected left and right turns, and recognize traffic lights and stop signs. It can also perform automatic lane changes, and it uses end-to-end neural networks to make driving decisions in real time. FSD is capable of handling roundabouts, pedestrians, cyclists, and unpredictable urban situations. However, even with these advanced features, FSD is still considered a Level 2 system. This means the driver must supervise at all times and must be ready to intervene whenever necessary. To summarize the difference, both Autopilot and FSD require driver monitoring. Autopilot is mainly for highway assistance, while FSD covers both urban and highway driving. including complex scenarios. FSD uses more advanced neural networks and more sophisticated behavior prediction compared to autopilot. In short, autopilot helps with basic highway driving, while full self-driving aims to handle the full range of real-world driving situations, but still requires human supervision today. In this slide, I will introduce what's new in Tesla's full self-driving version 14 and why this update is considered one of the biggest leaps in Tesla's AI development. FSD version 14 represents a major shift toward behavior-based artificial intelligence. Instead of relying on many separate modules, the system now uses a more unified end-to-end neural network approach. This allows the car to make decisions in a way that is more natural, more consistent, and closer to how a human driver behaves. Let's begin with the core improvements. FSD V14 shows much better decision making, especially in complex environments. Braking behavior has become smoother and more human-like. The system handles unprotected left and right turns with greater confidence. It also performs lane changes and turns more naturally than before. Intersection handling has improved significantly, and the system is better at predicting the movements of pedestrians and cyclists. Now, let's look at the technical enhancements. FSD V14 processes camera images at a higher frame rate, which helps the system react more quickly. Latency has been reduced so the car responds faster to sudden changes on the road. Camera-based depth estimation has become more accurate, allowing the vehicle to better understand the distance and shape of surrounding objects. Long-range tracking has improved as well, helping the car anticipate the behavior of vehicles far ahead. Path planning is more precise, and the system is optimized to take full advantage of Tesla's HW4 hardware. Finally, let's talk about why FSD version 14 truly matters. This update represents a major step toward behavior-based AI, where the system learns patterns from real human driving. As a result, the driving experience feels more natural, more confident, and more consistent. These improvements also move Tesla closer to its long-term goal of building a fully autonomous robotaxi network. In summary, FSD V14 brings major advancements in decision-making, perception, prediction, and overall driving behavior. It is one of Tesla's most significant updates, pushing the system closer to safe and scalable autonomous driving. In this slide, I will explain how Tesla's full self-driving system understands the world around it. The process is divided into three major stages: perception, prediction, and planning. Let's begin with perception. Perception is what the car sees. Using its camera system and neural networks, the vehicle detects other cars, pedestrians, cyclists, and the edges of the road. It also recognizes traffic signs, lane markings, and many small details in the environment. The system estimates depth using cameras only and builds a real-time three-dimensional scene of everything happening around the vehicle. Next is prediction. Prediction is what the car believes other road users will do next. The system analyzes nearby vehicles, pedestrians, and cyclists and estimates how they are likely to move over the next 1 to 5 seconds. It anticipates behavior, such as whether a car might merge or whether a pedestrian may step into the road. These predictions are learned from large-scale human driving data, allowing the system to behave more like an experienced human driver. Finally, we move to planning. Planning determines what the car itself should do. The system chooses the optimal path, adjusts speed and direction, and handles complex maneuvers such as lane changes, turns, and navigating through intersections. During planning, the system balances safety, comfort, and efficiency to create smooth and predictable driving behavior. These three stages, perception, prediction, and planning, are powered by neural networks that work together as one unified system. This integration helps the car react faster, brake more immediately when needed, and behave in a more human-like way. In summary, perception tells the car what is happening, prediction tells the car what might happen next, and planning decides how the car should respond. Together, they form the foundation of Tesla's approach to safe and intelligent autonomous driving. In this slide, I will explain how Tesla trains full self-driving using end-to-end neural networks, and why this approach represents a major shift in autonomous driving technology. End-to-end learning means that a single neural network handles perception, prediction, and planning all together as one unified system. Instead of relying on many hand-coded rules, the network learns driving behavior directly from real human examples. It outputs steering, braking, and acceleration decisions based on what it has learned from millions of real-world scenarios. Now, let's look at the training pipeline. Tesla collects massive amounts of data from its global fleet of vehicles. This includes video clips, driving behavior, and rare edge case situations. Human driving behavior is labeled to teach the network how skilled drivers react in different environments. The neural networks are then trained on Tesla's supercomputers, including the Dojo system. After training, the improved models are sent to vehicles through over-the-air updates, allowing the system to improve continuously. Next, let's talk about why this end-to-end approach matters. It is essential for Tesla's long-term vision of a fully autonomous robotaxi network. Instead of relying on manual engineering or thousands of separate rules, the system grows by learning from data. This creates a unified driving model that becomes more capable as more data is collected. There are also important benefits to end-to-end learning. Driving decisions become more human-like, with smoother turns, more natural merges, and better lane changes. The system handles rare or complex edge cases more effectively because it learns from real examples rather than predefined rules. And the improvement cycle is faster since the network can be retrained with new data instead of rewriting code manually. In summary, end-to-end neural networks allow Tesla to train FSD to drive like a human. The system learns from massive amounts of data, improves through continuous updates, and forms the foundation for Tesla's future autonomous driving capabilities. In this slide, I will explain how Tesla's full self-driving system makes real-time driving decisions and how it aims to drive like a skilled and confident human driver. Let's begin with smoothness and comfort. FSD is designed to accelerate and brake in a human-like way, avoiding sudden or uncomfortable movements. Steering inputs are natural and steady without abrupt corrections. The system positions the vehicle predictively in the lane and it reduces jitter or hesitation even in complex driving situations. Next, let's look at how FSD interacts with other road users. The system yields appropriately to pedestrians and cyclists, and it maintains a safe following distance from the vehicle ahead. It predicts the intentions of nearby drivers, such as merging or turning behavior, and it handles lane changes and merges in a cooperative and respectful manner. Now, let's move to real-time decision logic. Tesla's end-to-end neural network directly outputs driving actions, such as steering, braking, and acceleration. The system constantly balances safety, legality, and comfort while adapting to the flow of traffic. It refines its decisions continuously using data collected from the entire fleet, allowing the system to improve with every new update. Finally, let's summarize why this driving behavior matters. A more natural and confident driving style reduces the need for driver interventions. It also brings Tesla closer to a future where a connected fleet of autonomous vehicles can operate safely and efficiently as part of a robotaxi network. In summary, FSD's driving behavior focuses on smoothness, cooperative interaction with others, and intelligent real-time decision-making. Together, these elements create a safer and more human-like autonomous driving experience. In this slide, I will explain when and why a driver must take over while using Tesla's full self-driving system. FSD is a supervised level 2 system. This means the driver must stay alert, keep their hands ready, and be prepared to intervene at any moment. Even though the system is advanced, it is not autonomous. Let's begin with system-triggered interventions. These are situations where the car itself signals that the driver should take control. This can happen when the driver manually overrides the system or when the road becomes too complicated with unexpected obstacles. It may also occur when lane markings are unclear or missing, or when the car is driving in snow, fog, or strong sun glare. Four-way intersections, misaligned pedestrians, and general system alerts can also trigger a request for the driver to take over. Next, let's look at driver-triggered interventions. These occur when the driver decides that taking control is safer. For example, a strong steering correction from the driver will immediately disengage FSD. Pressing the brake pedal firmly will also override the system. Drivers may intervene when they feel discomfort or uncertainty, or when dealing with aggressive drivers or sudden turn-ins. Unique or unusual obstacles, such as unexpected animals or pedestrians, may also require manual control. Flashing emergency lights or hazard situations are another reason for the driver to take over. Now let's talk about why interventions matter. Interventions help ensure safety during uncertain or ambiguous scenarios. They also help Tesla collect valuable data to improve its neural networks. Interventions reinforce the fact that FSD is not yet autonomous and still requires human supervision. They are also important for meeting regulatory requirements in all regions. In summary, driver intervention is a critical part of using Tesla's full self-driving system. It keeps the driver engaged, helps the system learn, and ensures safe operation in challenging or unpredictable situations. In this slide, I will explain the current limitations of Tesla's full self-driving system and the situations where the technology still struggles today. Let's begin with environmental limitations. FSD relies heavily on camera vision, so anything that reduces visibility can affect performance. Heavy rain, snow, or fog can make it difficult for the system to clearly see the road. Low light conditions or strong sun glare may confuse the perception system. Dirty or obstructed cameras also reduce accuracy, and poorly painted or faded lane markings can make lane detection more challenging. Next, let's look at road and scenario limitations. Construction zones are one of the most difficult environments because temporary lanes and cones can change the road layout unexpectedly. Complex unprotected turns still require careful human supervision. Unusual intersections or roundabouts may cause hesitation. Unexpected behavior from pedestrians or cyclists can also challenge the system. Emergency vehicles, flashing lights, and sudden road closures are additional situations where FSD may struggle. Now let's move to system level limitations. FSD is still classified as a level 2 system, which means it requires constant driver attention and hands on the wheel. The system may occasionally hesitate or behave overly cautiously, especially in unfamiliar situations. It can also struggle with rare edge cases that are not well represented in the training data. Finally, let's talk about why understanding these limitations matters. Knowing the system's boundaries helps set realistic expectations and ensures safe operation. It also highlights the areas where Tesla continues to improve through software updates and additional training data. And importantly, these limitations reinforce that FSD is not yet autonomous and still requires human supervision to meet regulatory standards around the world. In summary, FSD has made significant progress, but it still faces challenges in harsh weather, complex road environments, and rare or unpredictable scenarios. Recognizing these limitations is essential for safe and responsible use. In this slide, I will explain the regulatory status of Tesla's full self-driving system in the United States and in South Korea. Although FSD is technologically advanced, it is still classified as a supervised Level 2 system in every region of the world. Let's begin with the United States. In the US, FSD is officially recognized as a Level 2 supervised system. There is no federal approval for fully autonomous driving. Instead, each state has its own rules, which means regulations can vary widely from one region to another. Robotaxi operations require separate permits, and only a few companies have received those approvals. The National Highway Traffic Safety Administration continues to monitor Tesla closely, conducting investigations and reviewing safety data. Over-the-air software updates must follow federal safety reporting rules to ensure compliance. Now let's look at South Korea. South Korea maintains much stricter regulatory standards. FSD is still considered a Level 2 system, and Level 3 approval is extremely limited. Tesla's full self-driving is not approved for autonomous use under Korean regulations. The country places strong emphasis on driver responsibility and liability. Any over-the-air update that affects driving behavior requires regulatory review before it can be deployed. This creates a higher barrier for advanced driver assistance features. Next, let's summarize the key differences between the two regions. The United States allows broader testing and more diverse deployment environments. South Korea maintains stricter certification requirements and stronger liability rules. Neither region recognizes Tesla FSD as an autonomous system. This creates a deployment bottleneck for higher-level automation. In summary, the regulatory landscape for FSD is still developing. The United States offers more flexibility, while South Korea enforces tighter control. Understanding these differences is important for setting expectations about when and how true autonomous driving may become available in each region. In this slide, I will explain why Tesla's full self-driving system is still classified as a Level 2 system and not Level 3 or higher in every country around the world. Let's begin with what Level 2 actually means. In a Level 2 system, the driver must keep their hands on the wheel and remain fully responsible for monitoring the environment. The system can assist with steering, braking, and acceleration, but it cannot operate without human supervision. There is no legal shift of liability from the driver to the vehicle. Now, let's look at why FSD is not considered Level 3 or above. Level 3 requires conditional autonomy, where the system can take full control under specific conditions without constant driver monitoring. Tesla has not received Level 3 certification in any country. The vision-only approach still faces environmental limitations such as heavy rain, snow, or glare. Regulators also require much more validation and redundancy before approving unsupervised operation. And because occasional interventions are still needed in complex scenarios, FSD does not meet Level 3 requirements. Next, let's examine the key regulatory barriers. In the United States, the system is classified strictly as Level 2 by the National Safety Authority. In South Korea, Level 3 approval is limited to a small number of manufacturers, and Tesla is not certified. In Europe, strict rules require hardware redundancy that Tesla's current system does not provide. Liability laws in many regions are also not aligned with fully autonomous operation. And Robotaxi approval requires a separate higher-level certification that Tesla has not yet obtained. Finally, let's talk about why this classification matters. It helps set realistic expectations for drivers and regulators. It clarifies that legal responsibility still belongs to the driver, not the vehicle. It highlights the gap between current capability and true autonomy. and it provides context for Tesla's long-term roadmap over the next several years. In summary, Tesla's FSD remains a supervised Level 2 system because of technical limitations, regulatory requirements, and the need for human oversight. Understanding this classification is essential for safe and responsible use as the technology continues to evolve. In this slide, I will walk you through Tesla's full self-driving roadmap from the year 2026 to the year 2030. This timeline shows how the technology is expected to evolve both technically and regulatorily over the next several years. Let's begin with 2026. By this time, FSD version 14 is expected to stabilize. The end-to-end neural network will be more mature, urban driving will improve, and complex turns will become more reliable. Tesla will also complete full optimization of HW4 across the fleet. Next is 2027. This is when Tesla plans to deploy its next-generation hardware platform known as HW5. It is expected to deliver over 1,000 TOPS of compute power, along with higher resolution cameras and Robotaxi-grade inference performance. This hardware is designed for large-scale autonomous operations. Now we move to 2028. This is the year when early Robotaxi operations may begin in limited regions. These programs will still require remote supervision, but they will generate large amounts of fleet data to refine the neural networks on a much larger scale. In 2029, Tesla may undergo Level 3 certification review in certain markets. This would allow conditional autonomy in restricted domains such as specific highways. Regulators will evaluate safety, liability, and fallback procedures. Even with approval, it would not yet qualify as Level 4, and human oversight would still be required outside certified zones. Finally, we reach 2030. This is Tesla's target year for fully driverless Robotaxi operation in approved areas. The goal is to enable scalable autonomous fleet services without human supervision, forming the foundation for global expansion. To summarize the roadmap, FSD remains a supervised Level 2 system today. Level 3 may become possible around 2029 depending on regulatory approval and safety validation. Level 4 and Level 5 autonomy will require major advancements in both technology and legal frameworks. In short, Tesla's roadmap shows steady progress, but true autonomy will take time, rigorous testing, and global regulatory alignment. In this final slide, let's review the key takeaways from everything we've learned about Tesla's full self-driving system. First, Tesla uses a vision-only architecture. Cameras are the primary sensors, and the system relies on neural networks to interpret the world in a way that resembles human perception. This approach removes the need for radar or LiDAR and focuses entirely on visual understanding. Second, Tesla's FSD is powered by end-to-end neural networks. These networks learn directly from real human driving behavior. As a result, the system becomes smoother, more natural, and more human-like as more data is collected. Third, Tesla's hardware continues to evolve. Today, HW4 powers the fleet, and HW5 is coming soon with significantly higher compute power. Each new hardware generation enables more advanced neural networks and more capable driving models. Fourth, we must remember the regulatory reality. FSD remains a supervised Level 2 system in every region of the world. Level 3 may become possible around 2029, but only in restricted domains and only with regulatory approval. True autonomy still requires major validation and legal alignment. Finally, let's look at the future roadmap. Robotaxi pilot programs are expected later this decade, but full autonomy will require stronger hardware, more data, and supportive regulatory frameworks. Tesla's long-term vision is a scalable autonomous mobility platform built on continuous learning and continuous improvement. In summary, FSD is not just an advanced driver assistance system, it is Tesla's long-term foundation for autonomous driving. The next breakthroughs will come from data, from compute, and from regulatory progress.